In this video, we're going to be discussing a way that we represent how the energy changes over the course of a reaction visually. So we use a type of diagram known as a reaction coordinate diagram or a potential energy diagram for this representation. So this is how we these show how energy changes over the course of a reaction. So in this type of diagram, the x-axis is labeled as reaction progress, or sometimes reaction coordinate, which is where the name comes from. And then the y-axis is chemical potential energy. So this idea of reaction progress is very qualitative on the x-axis. Essentially, just on the left, you've got the reactants, and on the right you've got the products, and in between you've got the stuff in between. We often think about chemical reactions as being more or less an instantaneous change from reactants to products, and thus far we haven't really talked about there being anything in between, but there is. The process of a chemical reaction, we've said, is bonds breaking in the reactants and bonds forming in the products. But when a bond breaks, your bond is your two atoms connected together. When that bond breaks, that is because your atoms gradually move farther and farther and farther and farther apart until they can't feel each other anymore. It's not like cutting a string with scissors. As you move them farther apart, the bond gets weaker until eventually it breaks entirely and there's no more attraction between those two atoms. Same idea in the other direction for forming bonds. As two atoms come close together, they start to feel each other and become more and more strongly attracted until they reach their bond length, which is where the maximum attraction occurs. And that is when the bond is fully formed. So we do have this process of breaking and forming, not just snap and it's done, that we need to think about. So in a reaction coordinate diagram, somewhere on the left we have a dot or a line, depending on how you want to draw it, representing our reactants, and somewhere off to the right we have the same thing representing the products. So everything we've been talking about in thermodynamics, delta H, delta S, delta G, all of our deltas, is dealing with the change or the difference between the reactants and the products. So thermodynamics is pretty much just looking at the difference between these two values. On a reaction coordinate diagram, this is usually representing delta H, is the difference between these two quantities here. And this is really all that thermodynamics talks about, all that thermodynamics considers. So thermodynamics only really considers the difference between the initial and final states, hence all the deltas. But it doesn't really capture at all, doesn't pay any attention to what's happening in between those initial and final states. So again, those initial and final states in the context of a chemical reaction are our reactants and our products. So that's all that thermodynamics is considering, is the difference between where we started and where we end up, but it doesn't consider what happens in between. And energetically speaking, this is important because it's not a straight line. As our reaction proceeds, our energy does not go directly from reactant to product. What always happens, actually, is that from our reactants, the first thing that happens is our energy goes up, and then it comes back down to wherever our products are. So our energy always goes up to some maximum that is higher than both our reactants and our products, regardless of how those energies are related. There's always a higher maximum in between, and then comes back down. So we've always kind of got this energetic hill in between our reactants and products that our reaction has to get up and over. So on this diagram, there are a few important points to talk about. The first one is this maximum. So this maximum energy point is known as the transition state. So the transition state is the highest energy structure that our reaction passes through. Now, transition states are high in energy, as you can see on the graph, and that means that they are not stable at all. Transition states do not stick around. As soon as they form, they break back down. That it is very much something that your reaction is passing through, not some place that it is going to stay. Transition states are weird to think about because they usually involve bonds that are half formed or half broken. Again, we're in the middle of this process of breaking and forming bonds. So the transition state is often in between a bond that existed in the reactants but is gone in the products. At the transition state, it might be halfway to broken, which is weird to think about. So this is why transition states aren't stable. It's because they have these things like half bonds that don't really exist normally. But it's an important passing point for our reaction because it governs this difference in energy here, which is known as the activation energy, which we commonly label EA. So the activation energy can be thought of as the minimum amount of energy to get a reaction started. And the activation energy is a really, really important thing to be aware of because it's related to the speed of a chemical reaction. Whether that reaction is going to be fast or slow. So the activation energy is the amount of energy you need in order to get your reaction going. If it is really high, your reaction is likely to be very slow, that there won't be very many particles that have enough energy to get up and over this hill. It's also referred to frequently as the activation barrier, that it is an energy barrier that must be overcome or surmounted in order to get from reactants to products. So the higher your activation energy, the slower your reaction is going to be under similar conditions. If you're comparing two different reactions under similar conditions, the one with the higher activation energy is going to occur at a slower speed. So this is a big part, or this is the main part really, of what thermodynamics fails to capture. That thermodynamics tells us about the beginning and ending states, but it doesn't tell us what's happening in between. It can tell us if something is thermodynamically favored, but it cannot tell us if it's going to happen quickly. That is something, this area in between is the realm of what we call kinetics. So this in-between zone oops. No. I'm doing poorly at this. There we go. The area in between is the realm of kinetics. And kinetics is entirely about reaction speeds. It is the study of reaction rates or speeds. And we're not going to get into kinetics this semester. We'll save that for AP Chemistry in the spring if you're doing that. But it's important to be aware that thermodynamics doesn't give us all of the information to know necessarily that a reaction is going to happen right away. Just because something is thermodynamically favored does not mean it happens quickly. So something may be thermodynamically favored, but if it has a really, really high activation energy, that process may be so slow under normal conditions that it doesn't really happen at a visible rate, that it doesn't really happen under normal circumstances. So I think of this concept as spontaneous does not mean instantaneous. So we use the terms thermodynamically favored and spontaneous more or less interchangeably in chemistry. But the problem with the word spontaneous, as we use it outside of science in the English language, conjures up this image of something happening right away, that if you make a spontaneous decision, you're going to go do something right now that you hadn't planned on. But a spontaneous reaction might never happen because it might be so slow that you just never actually observe the reaction happening. My favorite example of this is the conversion of diamond into graphite. So the conversion of diamond into graphite is actually thermodynamically favored at all temperatures. It is slightly exothermic and has an increase in entropy for that transformation as well. So it is thermodynamically favored at all temperatures, but as jewelry commercials like to tell us, diamonds are forever. Graphite is just the stuff in your pencil leads. They're both forms of carbon, but they are different three-dimensional bonding structures of carbon. So in the case of diamond and graphite, we have diamond here. Graphite is a little bit lower in energy. So this is a negative delta H. We're starting at a higher energy, ending up at a lower energy. Graphite is also higher in entropy. There are less connections, fewer connections between your carbon atoms, so they're able to move around more, which is more microstates. So we have a higher entropy in graphite as well. So this process is thermodynamically favored under all conditions, but what the thermodynamics fails to show you is that the activation energy for this process is absolutely huge. So the activation energy for this is like off the charts massive. So this reaction is so slow that under any normal circumstances, it just doesn't happen. So thermodynamics gives us a really important part of the picture for whether or not something is thermodynamically favorable, but it doesn't tell us the whole story. If we actually want to do a reaction in the lab, it needs to be thermodynamically favorable, or we need to be able to make it happen anyways. You can force non-favored reactions to occur. You just have to supply them the energy they need. But we need something with a reasonable activation energy, or a way to supply more energy if something has a really high activation, like this particular example. Reaction coordinate diagrams can also tell us some more detail about how a reaction happens, about how we actually get from reactants to products. Because some reactions don't go directly from reactants to products as we've written the equation. They can actually go through a series of multiple steps. So some reactions occur as a series of multiple steps, and we can see that in the reaction coordinate diagram. When we have a multiple step process, what we'll see is that each step along the way has its own activation barrier. So if something occurs as a single step, it'll look like the diagrams we've drawn so far that are just a single mountain, a single hill in between reactants and products. If something occurs as multiple steps, it's more of a little mountain range that will have multiple peaks, multiple activation barriers that need to be overcome in order to get all the way from reactants to products. So for instance, we might have something that looks like this, just as one example. So we've got sort of a split here between where we started and the first peak would be step 1 in this area in here. And then our second peak to where we finish would be the second step of our reaction. And we can have as many steps as the reaction wants to have. So this would tell us, if we saw this reaction coordinate diagram, that this reaction is occurring in a 2-step process. And again, each step has its own activation barrier. So we've got activation energy for step 1 here. We've got the activation energy for step 2 here. Each of these steps has its own transition state. So we have the transition state for step 1, we have the transition state For step 2, we can still assess our delta H for the reaction overall. And we also have, that's a terrible color. We also have, this be better? This is better. A new sort of point in here that is this energy minimum in between our two peaks. So this point is known as an intermediate or a reaction intermediate, which is just a substance that's formed in between steps in a multi-step reaction. So unlike transition states, intermediates can be stable depending on what they are. They're typically less stable than your reactants and products, but locally, they're a minimum, that on either side, these things are less stable than our intermediate. So they're a local minimum. They're relatively stable compared to the structures immediately before and after in the process. So sometimes they can stick around for a little while. And then the last thing to be aware of with reaction coordinate diagrams and with thermodynamics is how a catalyst affects your system. So let's get rid of this. When you add a catalyst to a chemical reaction, you likely learned about catalysts in biology when you talk about enzymes. So you know that a catalyst is something that speeds up a chemical reaction. So people often think about catalysts as being something that makes a reaction work better. So it is tempting to think that that would make the reaction more favorable, but all a catalyst is doing is affecting the speed. Thermodynamics has nothing to do with the speed. That is kinetics. So all a catalyst is doing is lowering the activation energy. It does not affect the thermodynamic favorability. If a reaction is not thermodynamically favorable, adding a catalyst is not going to help. If you have a reaction that is thermodynamically favorable but very slow, adding a catalyst will help. That it can speed up the reaction to a point where it's actually a useful speed. So how this affects the reaction coordinate diagram is it essentially just makes your peak shorter. The catalyst is like a shortcut that instead of going all the way up and over the mountain, you found a tunnel through the middle. So for example, if we have our reactant and our product, if our uncatalyzed version of the reaction looks like this, our catalyst is just going to make our mountain smaller. So there are any number of ways that that can happen. One possible catalyzed pathway might look like this. Still a single step process, but a shorter peak. So my activation energy, instead of being from my reactant all the way up here, is now from my reactant only to this height. Oftentimes, what happens is that your catalyst breaks down the reaction into a series of simpler steps, each of which has a lower activation energy. So rather than one really complicated step that you need a lot of energy to complete, you might end up with a multiple step reaction, each of which has a lower activation energy. Without additional data, it's not possible to know exactly what your catalyzed pathway would look like, but these are just some options for what can happen. So you should be able to sketch like one possible catalyzed pathway that just gets across the point that the catalyst lowers the activation energy, but it doesn't change what your reactants and products are, so it doesn't change the starting energy and it doesn't change the final energy. All it does is make the reaction go faster by decreasing the activation barrier.